Hello everyone, welcome to the first talk of this year. So we have today Malav over here, Malav Doshi, and his interests are in probability, and he will give a gist of talk on gist of optimal transport. Over to you, Malav.
Thank you, Sean Chandra, for the introduction. So today's agenda would be looking at the optimal transport, and this traces back into 1700s, where the first formulation was given by Monge in 1780. This was the first mathematical formulation which was given, but the theory of transportation and this problem was very prevalent since 1500s, 1600s. But Monge was the first one to mathematically formalize all the detailings of the optimal transport and give the basic formulation. And then Kantorivich during the like World War II was a Soviet economist which gave a better formulation, and let's see how we can tackle the both of the formulations. So with the problem, which was the first primal problem suggested by Monge. So suppose that there is this set of mines, name them, and this set of factories, name them. So here we have x1 to xn, and again y1 to each of the mine produces some amount of ore, and the goal of the problem is that each of the factories receive ore from precisely one of the mines, and every mine provides the ore to precisely one of the factories. So the mathematically what we want is a bijection from M to F. But now there would be certain conditions on the bijections. So I'll define certain notations. So we will define Cxiyj be the cost of moving ore from ith mine to jth factory. So if I go from x1 to x3, then this would be Cx1 y3, and we will see that during Kantorivich formulation I won't write this long expression, but this would be just replaced by Cij. But that we'll look at later. So what happens is that now the total cost over a map. So if I have a bijection from M to F, so if T is a bijection, then total cost for the given bijection would be over. This is the total cost which prevails when we go for each of the mines. So from every mine we want to go to one of the factories. So what we want is we want a map which minimizes this cost. So a primary discrete problem for Mons is basically minimizing over T, C of T, such that F is a bijection. This was the first mathematical formulation of optimal transport, which was a discrete case. So, well, after this, an obvious thing would be to find an analog of this problem into a continuous domain. So, let us look at the continuous Monge formulation. So what happens is that suppose that we have this two spaces, and this can be visualized as this is, let's say, heap of sand, and I name this space by chi or x, whatever, and there is this pit hole here having some shape denoted by script y. So our target is to move all of this sand into this hole, but optimally. So what do I mean by optimal is, so if I pick up a point x here, I will transfer this into some point y under a map T, and there would be this cost. So C would be cost of moving the sand from point from x to y. Sorry? Yeah, cost is a real valued function. So yeah, so next thing, so cost is not r square but the space. So yeah, so basically from x to y, this would be the cost of moving, and but now there has to be analog of measure or weight. So what would be the amount of sand? So I'll introduce two measures, mu on space x and mu on space y. When I introduce this measure, we have this underlying assumption that this comes from a density. So if I write mu of E such that E is a subset of X, this will give us similarly if I write mu of F such that F is subset of Y, it would be the mass of sand it can accommodate. So basically, this can be viewed as volume or as we say measure of the set. But there is this one remark which we won't be using for this whole talk. Whenever I write d mu of x, we assume that there is this appropriate density due to which this measure of mass arises. Similarly, when I write d mu of x, this can be, this is density over x, and this can be viewed as density over y. So this is just an underlying assumption. We won't be using this density thing. What we are concerned about are just these two measures, mu and nu. This can be viewed as marginals of x cross y. So now again the same problem prevails, that what we want is, we want a map from chi to y such that, now what would be the total cost? Total cost would be, before that let me just introduce you to the push forward measure. Okay. So suppose that this is a bijection which we already have. Well, now as I said that we can view this chi and x and y as the heaps of sand or amount of some things there. So there would be mass conservation which we will expect. So the total measure of this both space has to be equal. So we assume that there is no loss of the mass. So amount of sand here would be exactly equal to the amount of sand which gets transferred there. Sorry? Yeah, finite measure. Actually, we can extend these things into infinite, but then the problems actually won't make much sense. Then we need to go into abstraction, but these things are just related to the real life applied problems. So yeah, we can obviously get the analogs. So that T is a bijection and T is invertible. As I said that there has to be global mass conservation. Similarly, there has to be a local mass conservation. So if I pick a subset E and map it over some subset F, so we assume that amount of sand which we took from E has go to the exactly equal to F. So if T of E, or let's say T of A is B, then mu of, and this is what we will consider as push forward, but we won't go into the detail. So this is just the local mass conservation. So this ensures the global mass conservation, and this ensures the local mass conservation. So we can view these two things as our constraint, but this thing, so this is for all. So this local conservation obviously ensures us with the global conservation. So what happens is now our, if I have this point X, what I'll do is I'll take a very small region around it having mass d mu of x. Now cost of mapping this x to some y, to some t of x, is similar. So this would be our small element of the cost, and we will integrate this over x. So what our goal is to find minimum of over t such that so this is the continuous analog of Monge formulation. Well, now there is, I won't say there is a problem or a fallacy in this formulation, but we can do something better. And for that, I'll give a very simple example. Suppose that I have this two books here, and my goal is to transfer this from point A to point B. What Monge formulation says me that if I pick up some mass from a point, I map it somewhere, I need to put everything which I took into the same place. So if I take these two books here and I want to optimally transport it from A to B, this might be the optimal way. What Kantorivich suggested is rather than keeping these two books together, I can take them separately and move them separately so I can get a better cost. So what Kantorivich suggested that if I take let's say 1 kg of the sand from some point X, rather than mapping whole 1 kg to some fixed point, I can take 500 grams to some Y1, 500 to some Y2. So Kantorivich formulation allows the division of mass. So Kantorivich formulation, this allows us division of mass. So from point X, I can take some amount of sand and I can map it to Y1, Y2, Y3 and any number of points. So now our constraints will slightly change in the Kantorivich formulation. So let us just look at the first the discrete problem. So if I have the same thing, if I have let's say these are our mines, these are our factories. What in Monge formulation what we had is that each of the mine will go exactly to one factory. But in this case, ore from one mine can go to multiple factories, just the mass should remain the same. So I have this joint measure which gives amount GF factory. So as I said that let's say this X1 produced 1 kg of the ore, then it can happen that X1 first it gives Y1 200 grams, then Y3 some 400 grams, and YM some 400 grams. So that sum should be equal to 1 kg, but the whole 1 kg shouldn't be transferred to only one of the factory. So this is what pi will capture. Pi will just show me that how much amount of material I am transferring from one place to another. So I'll denote this by pi ij. And then I have the same definition which I'll denote by Cij, as I said. Well, so now what we will expect, as I said, that summation of the masses should be equal. So we'll expect this thing that mu of xi is termed as mu y and mu of yj known as mu j. Mu and nu are again the same mass measure, which tells us that mu of x1 would be in this case, let's say 1 kg. So constraints which we want to follow is so these are our constraints which I want this should hold, because like it's the exact same thing. So this basically sums that from one factory how much amount of the mass goes to every one of them. So basically it shows us the capacity of the mine, and this basically shows the capacity of the factory. Okay. Sorry. Yeah, pi is basically coupling. So as I said, it basically captures how much amount of ore or how much amount of sand goes from ith factory to jth factory. In this case, let's say pi of x1 by 1. Yeah, that's what we are going to. We want to, yeah, this is basically the Kantorivich formulation. Over pi we will minimize it, we will see it. Yeah, we know the marginals mu and nu, and we want pi such that their marginals are mu and nu, and we need to minimize it over pi. Okay, so yeah. So now let us look at the continuous Kantorivich formulation. So these constraints in continuous case transforms very easily. So we again will have pi of x comma y for all, so for all basically. And we will have our cost function. So what this constraints will transform in is pi of so this basically is the distribution function. We can view this as marginals mu and nu, and this as the joint distribution. Well, so now what would be our function which we would be minimizing? Again, we will look at the same thing. So if we have, suppose that c of x comma y. So if we fix a point x in our initial space, this was our pit hole, and we will look at all the possibilities where x can map. X can basically map on every y. So this would be over d pi. So for a fixed, okay, so now we will look at the continuous Kantorivich formulation. Well, the analogs are pretty simple. So again, there will be pi x comma y, which will be amount of sand transferred from point x to point y, and what we want is our marginals to be following the marginals of this joint distribution. So we have a mu and nu. So if mu and nu are suitably probability measures, obviously finite, and pi is basically the joint measure, and then you can view mu and nu as the marginals and pi to be the joint measure of mu and nu. Okay, so these are actually our constraints, that this 2 should hold and this should be strictly greater than or equal to 0. So now what would be the cost? So we'll do the same thing. We have this our heap here, and there would be a point x and our pothole here, so the point y. So we'll fix our x here in this space, and look at all the possibilities, that what is the costing of mapping it to maybe this y, this y, this y, this y at different places, and the cost over all y, and then this we did for fixed x, so we will integrate it over all the x. So basically the integral transforms on the joint space. Notice that in Monge formulation, our minimizer or our discrepancy lied in this map T. Here, our minimizing thing would lie over this pi. So we want a joint distribution such that its marginals are mu and nu, and it is positive everywhere, and this is minimized. So this is exactly what I will write here. So yeah, so Kantorivich formulation would be since pi is continuous. And what is this pi mu nu? Pi mu nu is basically collection of joint measure with marginal mu and mu. This is our space pi. So what we will ensure is that we attain a infimum on this space. So for that we will assume that our C is continuous, and the space over which we are minimizing, this is compact. So if f is a function from u to r such that it's continuous, u is compact, the infimum or minimum of f exists. So similarly in this formulation, what we will assume that this space pi, this is compact, and our function on which we are integrating c is continuous. So we will assume that is compact and c continuous. Okay, so this will ensure us that you can easily check it. It's not a big deal. Yeah, compact space of basically joint measures. So yeah. Now there is this important topic. Okay, so point is that over minimizing this over pi is in itself a very big problem, or it's very difficult to do that. So what we will do is now introduction. We will introduce the notion of duals. In linear programming, there is this notion of duals, and a very simple example would be helpful to understand what exactly duals mean. So suppose that I have this r square, so r2 basically. This is y, and I have this line here, x equals y. If I look at this side of the line, what happens is that my x is always greater than equal to y, and x is greater than equal to 0 and y is greater than. So if I define my function f of x to be x and look at the minimum of f of x over this part following this constraint, what I'll get is this line is a solution. Okay, but there is one more way to approach this problem, is from this side. So if I look at this area here, what will happen is x is always less than equal to y, and these three things hold. So now minimizing f over this space is equivalent of maximizing f over this space. So this is a very simple analogy for duals. I'll write the whole exact dual problem, and you can get an intuition on maybe some books which I'll mention at the end of the talk. You can get the intuition of duals, that okay, why duals look like this. So if in linear programming, dual formation. Okay, so if our primal problem is something like minimizing B transpose Y, well, understand that Y has to be the variable. Y is the variable vector. Such that, so minimizing over Y, such that some C and Y is greater than equal to 0. If this is our primal problem, our initial problem, it would be exact equal to, we will prove that it would be exact equal to dual of maximizing. Now this x is another variable which we will introduce. So they both will agree x would be equal to y on just the minimizer and on the maximizer. So they would agree on the optimal solution such that, and when I write these inequalities, and these are vectors, so it's just the component wise inequalities. So yep, this is the dual formation of the problem in primal, and if the primal looks like this. So let's get back to our discrete case. If we properly look at our problem, these were the constraints, and what we wanted to minimize was Cij, Iij over I comma j, such that should equal to mu I, and summation of Iij over I should equal to mu j. So our sole target for discrete problem is to find suitable matrices in vectors such that we can write our whole problem in this form, and that's what exactly we will do. I'll just mention the vectors and matrices. You can verify them by yourself. It's not that hard. So yeah. So what I'll do is I'll define Y transpose B pi 1 1 I 1 n. So basically we are writing m cross n matrices, m cross n matrix as a vector because we want to write it as a vector product. Similarly, we'll write our C1, Cm, and the matrix A will look slightly weird, but it is intuitive. So what we want is that when I sum over this first section, this should be equal to nu n. When I sum over this second section, this should be equal to mu 2. Similarly, and moreover, when I take all the first values, pi 1 1, pi 2 1, pi 3 1, this should give me the marginal new measure. So we will exactly make our matrix look like this. So this would be of length m, this would be of length n. So what will happen is that here it would be just ones, 0 otherwise, ones, 0 otherwise, and so on. And this would be just diagonal matrices, because summing upon pi11, pi21, pi m1, it is equivalent of summing the diagonal entries if I write this as a matrix. So this would be just combination of the diagonal. So this is what our A will look like. And as I said that x is different from y. Notice that what we are minimizing is over this y, our basically joint distribution. So now we will introduce our new variable x, which will work as the minimizers or maximizers, sorry. It's maximizers first. So I'll write x to be u1, um, v1, v. So this is our new variable over which we will maximize our problem, our dual problem. So let us see the dual formulation. So this are the a, b, y for the primal case, and inputting them a, b and c here, what I'll get is something like maximize over sorry, c is basically the yes, just a second. Oh yeah, A transpose Y is basically our marginals, right? So yeah, so A transpose Y, sorry, very sorry. So when I write A transpose Y, what it will do is it will sum pi11 up to pi1m. No, no, no. These are U and V. So yeah, C. Thank you for telling. So yeah, C would be mu1 up to mu m, mu1 to mu n. C is just the collection of the marginals. Yeah, thank you. So yeah, our new problem will look something like over J such that this constraint holds. This is function u and v. Only this. And now as we do that, this is our discrete dual problem. So this is our dual problem. We will take the exact integral analog of how it will look like. So our primal problem looked something like this, and we look at the primal continuous problem of Kantorivich formulation. So our dual continuous Kantorivich will something look like maximize over u and v such that u of x plus v of y this whole. Well, I did nothing, just I converted this summations into the integral. So this where there's the discrete you can view as the point masses. Instead of point masses, we take the d mu analog of the integrals. That's what we did. Okay, so let us just formally write our dual problem in okay, so this is what our dual problem will look like. And as I said that when I introduced you to duality, I said that what we want is that minimal of our primal problem to be equal to maximal of our dual problem. We will prove this, we haven't, so I'll put a question mark there. Before that, let us prove a simple inequality which is known as weak duality. So weak duality basically gives us this inequality, and then we will do more manipulations to get into the exact equality. So what I'll write is, so I pi denotes our primal problem. We want to minimize over pi. So yeah, this is our primal problem, and this j u comma v is our dual problem which we want to maximize it. So this is our dual problem. Well, we know the constraints for our dual problem, that u of x plus v of y should be less than cx comma y. So if I'll just write that inequality here, but before that, we know that the marginals of pi for y, this should be equal to the mu of x basically, and marginal over d pi over pi should be equal to d mu. So I'll replace this d nu and d mu by this integral. So what we will get is our juv would just be double integral u of x plus v of y d pi. Well, this were marginals. What I did is just took the other measure other marginal, and got an integration. Similarly, here I had only one marginal I introduced the other marginal and took the integral. So it will form our joint distribution. So this is what our ju comma v will look like, and from the constraints which we have, so what were our constraints? Constraints was u of x should be plus v of y should be less than equal to c of x. So I'll just embed that inequality here. So what I'll get is j is less than equal to integral over, well, but this is what we defined as I pi, right? This is what we defined as our I pi. So what we got is that for all x comma y, notice the fact that we didn't use the nature of either u, v or pi here. The only thing which we used was just x and y. So we can just maximize this over u and v, which implies so this is what our weak duality is. And now we mathematicians are always greedy. So what we want is that, can we get the equality here? And we will see that under some special, not some special, in almost every condition where just some convexity holds and what we know as minimax principle holds, we can get an equality here. So let us just look at that. Okay, so if I write inf of pi, I pi, where pi belongs to this marginal thing, this would be equal to so we did nothing else. This is just kind of an indicator. So if pi will belong to our space, we will add nothing. But if pi does not belong to our space, we will add infinity. But the infimum wouldn't get affected by this infinity here. Okay. So now what we want to do is we want to replace this function 0 if pi belongs to nu and infinity otherwise by some function of ju, and that's what exactly we will do. So what I'll write is I'll just write one more thing, that is supremum of basically ju comma v minus b. This is just 0. I'm just adding and subtracting the same thing which we got here. But now notice the fact that if pi belongs to this pi, this our space of the marginals, then this will give us 0. Suppose not. Yeah. Yeah. So like no, here we are not taking it over pi. I just wrote infimum over pi. This of this function, I am claiming that if I take infimum of I pi over this space, it is equivalent of taking infimum over all the possible pi's of this set. So this it is basically equal, right? Because infinity will get added if pi does not belong to that space. So yeah, if marginals would be mu and nu, this will exactly equal to 0. Suppose not, then if suppose that our pi does not belong to this space of the marginals and this evaluate to something, let's say k, which is not equal to 0, well then I can, since u and v are arbitrary, I can just replace u by mu plus minus mu and plus minus mv in order to get my integral to be equivalent to mk. So if not 0, then I can replace this u and v by proper scaling, and taking the supremum will give me infinity here. So again the same thing arises, that so if j u comma v minus this integral, if this evaluates to k not equal to 0, I'll just uh, plug in, since u and v are arbitrary, change the function uv to plus minus mu and plus minus mv. So when I'll plug in this here, what I'll get my new value as plus minus mk. So if I take the supremum such that k is not equal to 0, that supremum will go to infinity. So I can replace this function by just, this is equivalent of writing supremum over u comma v okay. So when I write this function instead of this function in this set, what I'll get here is so what I'll get is in over pi sup over u comma v. Notice the fact that I'm replacing this function by this function supremum, and the I of pi does not depend on u comma v, so it's equivalent of taking supremum outside. I won't justify. I'll switch this supendence. This comes from something known as minimax principle, and we'll assume that minimax principle holds, which generally holds for nice functions like convex functions and continuous functions. We don't need much of the assumptions on the function, but at the end of the talk, I'll give you the reference where you can find the whole proof why you can switch this, but it's not meant for this talk. So if I assume that minimax principle holds, and I can switch this supendence, well, now looking at the constraints, we already have that u plus v is less than equal to c. Okay, so what we will look at is just supremum of u comma v. Now we don't need to worry about this other two factors. What we will just look at is as infimum over. So I pi will give us this c, right? So infimum of pi over u plus v minus c. This is what this c we got from I pi, because I pi was just c. Okay. Well, now just look at this. Sorry, b c minus 2 plus v. Very sorry. We assume that u, v, c are just continuous, and of course pi is the positive measure. So when we take the infimum, so pi has to be greater than equal to 0. So this infimum of this whole thing will go to 0, right? If we have proper constraints that c, u and v are finite functions and c, u and v are continuous functions. So if pi is ever greater than equal to 0, then if these are bounded also, or these are just bounded over the interval, then we can take this infimum to 0. So what I will get is infimum of, so supremum of infimum over pi of c d pi minus c minus u plus v d pi is equal to 0. Well, now notice the fact that only thing which we want to do, I can now replace this u plus v d pi again by so what I'll get here is that so u comma v in pi c d pi is equivalent of so u comma v in pi of j u comma v. And we know that we can write j u comma v in such a manner that it does not depend on pi, just depends on the marginal, which implies that inf over pi, and this obviously does not depend on u comma v, so this is what we claim to be strong duality. Modulo just one step which I didn't prove here, minimax principle, but as I said, I will give you the reference at the end of the day. Now we proceed towards the final result of this our talk, or of this talk, but before that, just one more introduction, then we can prove our final result. So now this result is known as strong duality, and this strong duality is not just one theorem. This is actually, I should say, bunch of theorems where you have notion of this dual and primal. One of them is max cut min flow, that or max flow min cut. Yeah, so that max min theorem, and that is also one of the form of this strong duality and weak duality. So the introduction to Legendre Transforms. So Legendre transform is given for all functions. We will restrict ourselves into the convex domain. So, so if I have a function here, it's a convex function. I have this line y equals mx. So what Legendre transform if star m captures is the longest or the maximum difference between the line and the function. So in this case, it could be, I guess, this. So f star m is defined as supremum over x. So how much a function below a certain line, what is the maximum distance between the line and the function, in where f is any function, but we will restrict ourselves into the convex case. So in convex function, we can always find a line above the function. We want to see that, okay, how much is the gap or how much is the distance between the function and the line, and this is what the Legendre transform is. Now there are some easy properties which you can verify. F star is convex. Doesn't matter whether f is convex or not. F star is convex. Now the one more thing is that if, let's say, I have one function g here, so that g is always such that g is always less than equal to f. So since g is less than equal to f or a fixed line, it would be more far than f itself. So that's the result. If g is less than equal to f, implies f star is less than equal to f. Actually, this is double implication, but okay, not do that. Okay, and simple thing is that f is always greater than equal to f star. It just comes from the fact that we are taking the supremum. So this is just the Legendre transform, and why this is used is that if we are working with the convex functions, it is always nice to look at the lines above the functions, which we can use it. So now there is this notion of subgradient. So when we have this non-differentiable function, let's say like mod x, and we don't know the derivative. So what we will do is that if I have a continuous analog of this function, the tangents would always lie below the function. It won't cross the function twice. So what we can define as subgradient is basically all the possible lines which pass through this non-differentiable point and stays below the function. So that's what our del f of x is, which is p such that okay, so subgradient basically captures all the line which stays below the function and passes through this non-differentiable point. And why we introduce the subgradient? Because there is this theorem that f of x sorry p such that this holds f of y greater than or equal to f of x minus xy. P is basically the real number, right? So you can view it as a slope. So when we have the continuous differentiable functions, p would be slope of each of the lines. Okay. But here, sorry. Very sorry. Very sorry. Very sorry. Actually, this is wrong. I'll get something else. So this would be plus e times y minus x. Extremely sorry. So you can look it as the, see, when we take the derivative, what we do is look at this slope, right? So this would be our slope p. So now we capture all the possible values of this slope such that the line remains below the function. So that's what with this p. So if I just take this side, so instead of this equality, I'll replace it with the inequality. Okay. Sorry. So, so yeah, this is our proposition which is easy to prove. F of x plus f star of y is greater than this, and equality holds if and only if y belongs to. This is actually very simple to prove. I'll just 3 lines, so I'll probably write it. Now ensures us that for all x, okay. So you have just expand it z x y minus f of x greater than equal to now this is for all z. So take the supremum over z. So xy minus f of x this is what, this is nothing but equal to f star of y. Actually the inequality would be the other way around. I suppose from z is yeah, so inequality would be other way around. Extremely sorry. We go like this. Yeah, which implies that f of x plus f star of y, and if y belongs to del of x, we will obviously have that f star of y equals xy minus x. Actually, this result we won't be using in proving the fact of our final result. So yeah, concluding the talk with our final result, it's simple if after introducing this all this stuff here. So our final result is for a Euclidean, not Euclidean, but a very special cost function. But I'll state one more result just. We'll prove this result for whole square. But I'll state the result at the end of the, after this, proving this result, which holds for any convex function h. So if c of x comma y is this, where h is convex, then there is a very nice result proven by Reshev and Shudov, which I'll state at the end of after this, proving this result. So now suppose that our c of x comma y looks something like this. So final result. So if c of x comma y looks something like this, so well, what would be our dual problem? So dual problem would be this is what we want to maximize it over. Maximizing over j is equivalent of minimizing over minus j. So if we do that, what we'll do is we'll replace our, we'll introduce two functions phi and psi such that u of x equals x square and so this is nothing but just scaling up or like just linear translation of the functions. So negative. Okay, so well, since these two would be, when we will integrate over u and v, this will give us nice integrals. So rather than minimizing over the whole, this whole psi minus half x square and phi minus half y square, it is just enough to minimize over phi and psi, just this integral. Which I'll term as phi and psi. Okay, well, constraints were simple. Constraints is u of x plus v of y, and in terms of phi and psi, what we will get is that phi of x actually this would be, I guess, the this equality only. There was some flaw in the proof. uh, I'll I don't know, like there was some flaw in the proof because due to the negation sign. But yeah, this inequality holds actually. So I don't know what was the flaw actually. So there was some minor, I guess, addition or subtraction flaw in the proof. So you can just work it out yourself, but yeah, this will hold. You can work it out yourself. This inequality. Okay, so now what I'll define is Okay. Well, now we know that this inequality holds. We have xy here, and we know that this inequality holds. So we expect that our solutions might look like LF dual. LF dual is basically if so we expect that our solution might look something like this. So dual of the dual. So and this actually equality holds when phi and psi are convex. So this would be equal to psi star psi if it is convex. Yeah. So this holds. So we expect that our pair should look something like this. Okay. So and actually that is true that for feasible solution, if we assume that these phi and psi are this is what we expect. So if we assume that okay phi and psi are not LF duals, so from the facts which I wrote here, I guess I erased them. But yeah, from the property of Legendre transform, it was clear that I of x y, which implied that okay, this hold for all y. So size so for all x comma y. So this will guarantee us this from the defining property from the proposition which we used, and from the property of the LF transform which take the supremum of the function. It will help us in writing this. Psi of y is greater than equal to psi star star. So these two comes from one comes from the proposition which we prove, and one comes from the properties of the LF transform. Well, so what we got? If we assume that phi and psi are not LF duals, we got two functions which are always less than these two psi star of x. So we got two functions which are LF duals, which are less than these functions. So these two pair optimizes our problem at least as much as phi and psi. So if we assume that the optimizing solution is not convex duals, we ended up proving that we will get a convex dual, LF dual, which optimizes our problem even more. So from this we conclude that our optimizing functions are in fact LF duals. So this was the main result of this talk. And as I said that there is this generalized result which I'll just state and then we'll conclude the talk. So the generalized result works for, so I'll state in terms of probability measures because all the measures which we are using are finite and their integration is finite, so you can always rescale them. So this result was given by Rashev and Roshan in 1998, such that if c of x y is function this where h is convex and your mu and nu are probability measures such that at least first moment is finite. Then we have this result that, and f mu is the CDF of mu. We assume that f mu is continuous, and f nu is CDF of mu. So our optimal map T would be just from R to R. Yes. This is the first result. This is our optimal map. And in the Kantorivich formulation, minimizer pi over of I pi would be just this was the result proved by Reshev and Revenshdorf in 1998. So this basically generalizes the uh, optimal solution for any convex function h, and its dependency should be linear in x minus 1. Okay, so yeah, any doubts, any suggestions?
Okay, so we can have few questions for Malav. One has.
Yeah, references. Okay, so references are there is this book by optics in optimal transport by Cedric Villani, and there is this lecture series by on optimal transport. And in this book, you will find the minimax principle in the first chapter itself. I believe it is page number 23. I don't exactly remember. But yeah, you can find that proof of switching the limits supendent in this book. So these are the two references. There are also other books by Cedric Villani. Yeah, these are the basic two books.
Okay, so I have a question actually. So all you stated are the results in the continuous cases. So are there results in discrete case also?
Well, that's a nice question, but the point is, you can, I suppose that you can find the results as an analog of this continuous cases, but generally discrete cases are harder to handle in these cases because here we have the nice properties of functions and this duality. So what we want to do is that we would then need to define this notion of subgradient and Legendre transforms in these discrete cases. So there are few results. I'm not much aware of it, but yeah, there are few results.
Okay. So if there are no further questions, you can thank Manav.